So this will give us the total number of ways in which we can distribute our particles, in which we can arrange our particles. Now this is of course not easy to understand this thing unless we consider an example on this one. And you remember that in the very first class we have solved the example of three particles. Now we will start with that example and we will check on these calculations that whether we have derived the general case right or not. So the three particle example, let me summarize that a little bit. We knew that we were having one particle in n infinite square well, and we were having three particles in n infinite square well, and one particle in one state, so the degeneracy was equal to 1. The energy was EA plus EB plus EC equals nx squared plus ny squared plus nz squared pi square h bar square over 2ma squared. And for this we took the example nx squared plus ny squared plus nz squared is 363, and we considered this is not right is with xy but right with ABC, as I am considering ABC here. So all these will be with A and B and C. So the NA, NB and NC three particle case, we remember that we can get 363 by squaring 11, 11 and 11. Then we were having 13, 13, 5, which can be arranged for distinguishable particles is 13, 5, 13 and 5, 13, 13. And another way was 1, 1, 19. 1, 1, 19. So this can be 1, 19, 1 and 19, 1, 1. And the last was 5, 7, 17. 5, 7, 17. So it can be 5, 17, 7, 7, 5, 17, and 17, 5, 7, 17, 7, 5, 17, 7, 5. 1, 2, 3, 4, 5. It was with 6 number of ways. So 5, 17, 7, 7, 5, 17, 7, 17, 5. 7, 17, 5. So we remember that one way, one configuration. The total number of ways this configuration can be arranged in one way. This one with not to write this one, but one way to do this thing. This is actually our Q value. The Q value that we have here, this is that value. This for this we are giving three ways to arrange this, three ways, and here we are having 6 ways. So we can verify here that our Q1 is 1, our Q2 is 3, our Q3 is 3, and our Q4 is 6. So we can now verify this thing with our relation, and our relation is the generalized result is this one. So here the Q N1, N2, N3, and this is equal to N factorial product and n running from 1 to infinity, and here the degeneracy. And in this example we consider the degeneracy equal to 1. So this will become 1 here over n, and the n here is actually equal to 3. So n3 we are having sorry, not 3 here, but this is n factorial, and this one I will now put in the values in this one further. So let's do this thing. How many total number of particles we have? How many total particles? We have total number of 3 particles. So this implies that we are having total number of 3 particles. The degeneracy is 1. So I have already put here, and for all the states. Now this I can simply write that this is equal, 3 factorial is equal to 6, and n is running from 1 to infinity, 1 over n factorial. So this is our simplified result, and now we will calculate our Q's, the number of ways. So in configuration number 1, which is this one, configuration number 1. This is our configuration number 1, configuration number 2, and configuration number 3 and 4. So in configuration number 1, we are having n11 equals 3. So in configuration number 1, we are having n11. So it is only 11. So 11, n11, they are 3 here, and all other ni's are 0. Other ni's are 0. Like we are not having n1 there, we are not having n2, n3, n4, and so on. So all other ni's are equal to 0, while n11 is repeated 3 times. So we are having that equal to 3. And what about our Q here? So our Q1, because this is configuration number 1, this is equal to 6. Q1, this is equal to 6, and all other n's are 0, and we will write like n1, n2, n2, n3, n4, and so on, is they are 0, so 0 factorial is equal to 1. sum in multiplication, it will not come to 0, but 6 multiplied by 1 over n11 n factorial. And this is 6 divided by n11 is 3n factorial, and this is equal to 1. So our Q1 came out to be 1. Only in one way this is possible. Similarly, in configuration number 2, this is configuration 1 and this is configuration 2. We are having, this is 13, 13, 5. So we are having n5 equals 1 and n13 equals 2. And now we will calculate that what is Q2. So 6 multiplied by 1 over, all the rest are 0, so 0 factorial is again 1. Only we are left with 1 over n5 factorial and 1 over n13 factorial. So this is 6 multiplied by 1 over n5, so 1 factorial, and 1 factorial is 1 multiplied by 2 factorial, and 2 factorial is 2. So 2 and 1, 2, and simplified with this we got 3. Similarly, in configuration number 3, we are having n1 equals 2 and n19 equals 1. So it will be the same thing, 2 and 1, 2 and 1. So Q3 is 6 multiplied by 1 over n1 factorial, which is 2, and 1 over n19 factorial is 1, and again we got 3. In configuration number 4, we are having n5 equal 1, n7 equals 1, n17 equals 1. So what about Q4? Q4 is 6 multiplied by 1 over 1 factorial, 1 over 1 factorial, and 1 over 1 factorial. So we got 6 here. And it seems that our generalized result, which we obtained from the general case, is true. We got the same number of configurations, we got the same numbers of possible combinations, the number of ways in which we can arrange these particles, and with this our generalized case for the identical particles is completed. We now start with case 2, and it is for identical fermions. About fermions, we are having these 3 statements. As we know that they are identical particles, so it doesn't matter which particle is in which state due to the identical nature. And there's only one n particle state with specific set of 1 particle state. And only 1 particle can occupy any given state. We know the Pauli exclusion principle that 2 fermions cannot be in the same state. So we will now pick our n1 particles out of the d1 choices. So let's start that we are having d1 equals 3. it means that degeneracy is 3. So we are having psi 1, psi 2 and psi 3. We are having 3 states which are having the same energy, and that energy is E1. Now, if I want to pick N1 equals to 1 particle, then how many choices do I have? So for N1 equal to 1, we have 3 choices. And the 3 choices are that I can put 1 particle in psi 1, 1 particle in psi 2, and 1 particle in psi 3. So I have these choices. I can put it in psi 1 or psi 2 or psi 3. And if N1 is 2, that I pick 2 particles, then how many choices do I have? So again, we are having 3 choices. How? That I can put 1 particle in psi 1, another particle in psi 2, then 1 particle in psi 2, 1 in psi 3, and 1 particle in psi 1 and another in psi 3. But if I have 3 particles, means N1 is equal to 3, then how many choices I do have? Then I have only 1 choice, and the choice is that I will put in each state 1 particle. So I have only 1 choice. And if I have N1 is equal to 4 particles, then I pick 4 particles and I want to put in 3 states. Then for fermions it is not possible, so I have 0 chance. Or I can say that no such combination can be built. No such combination can be built for fermions. Is it not possible to put more than 1 fermions in 1 state? So the number of states are 3 and the particles are 4. So such a combination is not possible. So I can means earlier we were having to pick the earlier question or the thing that we were doing was that how to pick N1 particles from N particles. This what we did earlier, and now it depends on the number of states for the fermions. So I will say that now our question will turn to that how to pick N1 particles, out of D1 states. Some they are dependent on the states, and I can write that means for this question, for the previous I had that the answer was for this is n factorial divided by n1 factorial n minus n1 whole factorial. Now this will go, n factorial will go to d1 factorial, and then means is I picking N1 particle, so what is the situation of d1? Divide by n1 factorial, and n, for this n I will again write d1 minus n1 whole factorial. So for the fermions, it will become like this. And the reason we know from here that there was no restriction on n, but here our n1 that we are taking is dependent on d1, the number of available states.